Hey everybody, let's talk about Lewis structures. So Lewis structures are a way that we are able to designate what molecules look like, not in a three-dimensional sense, but just kind of what they look like in terms of their arrangement. And in particular, we're interested in where the valence electrons are located within the molecules. Now, we are going to do some tricks. We're going to indicate electrons that are shared as straight lines. They'll look like hyphens, so they'll look a lot like this. Whereas lone pairs, pairs that are not involved in a chemical bond, we will indicate like this, a pair of electrons, just two dots. So remember that we're always trying to fulfill the octet rule. The octet rule states that we're trying to get 8 electrons, and we can do that by gaining electrons, losing electrons, sharing electrons, but our goal is always to get 8. And you see here this really nice list of rules for drawing Lewis structures. So you can absolutely come back here, you can reference that list, but I think the best way to show this is just with some examples. So you'll notice on your note guide, we're going to head down to page 10 on the note guide. I'm going to join you in going there. We're going to do 4 Lewis structures together, and we'll talk through these rules just on that page. The other thing that you need to do is make sure you have a periodic table. So if you don't have a periodic table in front of you, grab one now, pause the video, come back. We are going to try the Lewis structures for these 4 molecules. So PCl3, the first thing to do is that we are going to identify how many valence electrons we need to represent in this structure. Remember, we're drawing a picture of where the valence electrons are in this molecule. And if you remember back a few videos, we can actually identify the number of valence electrons in this molecule based on what column its atoms are found in. So on the periodic table, if you find phosphorus, you'll notice that phosphorus is in the 5th column over from the left-hand side. So here's what we're going to do. We're going to make a little calculation of valence electrons up here in the corner. We have phosphorus. How many phosphoruses are there? Well, there's 1 phosphorus. How many valence electrons does it have? Well, it has 5. So 1 times 5 means that for phosphorus, we are going to show 5 valence electrons. There are also 3 chlorines. So we have Cl, there are 3 of those. There are 7 valence electrons for chlorine. 3 times 7 gives us 21. If you add those together, we need a grand total of 26 electrons represented on our Lewis structure. Now the next thing that we need to do is actually draw out kind of a skeleton of what our structure is going to look like. So you see there it's PCl3. The first question is what arrangement to put these in. So here are some options. We could draw this thing like this. Right, there's an option. We could draw this thing like this. We could draw it like this. Right, so there are all these different permutations of how you could draw this. It turns out that we always put the least electronegative atom in the middle, which is very often the one that is drawn first. So phosphorus needs to go in the middle. There's some other clues here. On your periodic table, if you think back to electron configurations, chlorine has 1 place for an extra valence electron, so chlorine really only likes to make 1 bond. So because this chlorine is making 3 bonds, that's not going to go so well. Over here, these chlorines are going to make more than 1 bond as well, so that's not going to go so well. Similarly, phosphorus has 3 homes for its valence electrons, right? It has 3 vacancies in its p sublevel, so it wants to make 3 bonds. So for those reasons, really this structure down on the bottom, and I'll redraw it in the middle for us, this is going to be our structure. And another note here that you'll see in the rules is that whenever possible, if you can be symmetrical, if you can have symmetry in your molecule, that's valuable. So you'll notice if I draw this phosphorus in the middle and surround it with 3 chlorines, we have a great deal of symmetry around that phosphorus, and so everyone's happy. Now, I've drawn those lines in to represent bonds, but remember those bonds represent a shared pair of electrons. So even though we're drawing that as a bond there, another way of doing this, and you don't need to, would be to draw it like this, right? There are really 2 electrons for each one of those lines. Now that's not really the convention, so I'm going to keep my lines, right? I'm going to keep my bond lines like so. But it's really important for us to know that every time we see a bond, that equals 2 electrons. So let me redraw that because that's really confusing. One bond equals 2 electrons. So of these 26 electrons that we need to show, we have 3 lines drawn. 3 lines means 6 electrons. 3 times 2 is 6. So we've drawn, of our electrons, 6 of them already. We need to draw in the remaining 20. So how should we do that? Well, what we're going to do, this is the next rule, we are going to start with the terminal atoms, that means the outside atoms, and we are going to fill them up until they have a total of 8 valence electrons apiece, because everyone wants 8 valence electrons, right? So chlorine has 2 electrons right here. We are going to give it 6 more. There's 2, 4, 6. Now it has 8. This chlorine has 2, 4, 6. Now it has 8. This chlorine has 2, 4, 6. Now it has 8. Let's take a timeout and let's identify how many electrons we've drawn. Well, there are 8 electrons around this chlorine. There are 6 from the lone pairs and 2 from the bonds. 8 around that one and 8 around that one. So 3 times 8 means we've drawn 24 electrons. You'll notice that there's no room on these outer atoms to draw any more. I can't come in and like put 2 extra electrons on this chlorine. Why? Because now it has 2, 4, 6, 8, 10 valence electrons, right? We don't want it to have 10 valence electrons. We want it to have 8. And so if you run into a situation where you fill up those outer atoms, then you need to come back and you need to put those extra electrons on the middle atom. So here they are. Once we've drawn those, you'll notice that there are a grand total of 26 electrons. Remember that every single one of these lines represents 2 electrons. So if we go around quickly, we have a grand total of 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and 2 more there. So we have a grand total of 26. How do you know that your Lewis structure is done? And this is a really important point for a lot of people. There are 2 things you need to check. So I'm going to draw them just down here in the corner for us so we're aware of them. 2 things we need to check. Number 1, do all atoms have a full octet? And ours do, right? So all the chlorines have a full octet, they all have 8, and this phosphorus has 2, 4, 6, 8, because every bond counts for 2. So that's true, that's good, we've fulfilled that rule. Secondly, all of your valence electrons need to be shown. So what do I mean by that? The very first thing we did in green up here on the upper left is we calculated the number of valence electrons we need to show. It was 26. You'll notice that we've shown 26 valence electrons because we've shown a bunch of dots, right? We've shown 20 dots. We've shown 3 lines, which represent 6 electrons, so we've shown all 26. As soon as you've done both of those requirements, you have fulfilled the requirements of a Lewis structure. Now, just a heads up, it's not as simple as always just putting the dots in so it makes sense. We need to follow these rules in order, as you'll see when we get down to CO2. But let's try another kind of more straightforward one. Let's go over to CH2Cl2. We're going to follow our rules in order. We're going to start by calculating valence electrons. So we have a carbon. There's 1 carbon. How many valence electrons does it have? Well, it has 4. So we need 4 for carbon. There are 2 hydrogens. Each hydrogen has 1 valence electron, so 2 times 1 is 2. And there are also 2 chlorines. And we said chlorine has 7 valence electrons. It's in column 7. 2 times 7 is 14. If we add all of that together, we need to represent a grand total of 20 valence electrons. Now, CH2Cl2, again, we're looking for symmetry. We are looking for a situation where our least electronegative atom is in the middle. So the best way this thing is going to come together is with a carbon in the middle, surrounded by 2 hydrogens, surrounded by 2 chlorines. You could have easily made the chlorines going horizontally and the hydrogens going vertically. It doesn't matter, but ultimately you're looking for symmetry if possible. This is a great example to take a timeout when we're talking about the octet rule, and note that for both hydrogen and helium, and really hydrogen's the one we're going to use because helium doesn't bond. Hydrogen has something called the duet rule. So it's not singing, it's not that kind of duet, but hydrogen, it turns out, is happy with 2 valence electrons. So you'll notice if you have your periodic table in front of you that hydrogen and helium are kind of in their own row, right? There's only a 1s. Said another way, if you're doing electron configurations, you go from the 1s level that can hold 2 electrons directly to the 2s level that can hold 2 electrons. There's no 2p. So really there are no valence electrons, or sorry, there are only 2 valence electrons in the first energy level. So hydrogen is actually happy with 2 valence electrons. You'll notice that both hydrogens have a bond going to them. That bond represents 2 electrons, as we said, so both of these hydrogens are good. They have their octet, really called a duet, but we can't really touch them. We've shown of our total 20 electrons, we've shown 8 of them already, right? 4 bonds times 2, 4 times 2 is 8 electrons that we've shown already, which means we have to show 12 more. Now let's do that by adding to our terminal atoms first. So this chlorine needs an octet. We'll give it 6 valence electrons to complete its octet. And similarly, this chlorine needs its octet. We'll give it 6 more to complete the octet. Let's take stock of where we are. So hydrogen on the left, it has a duet, it's satisfied. Hydrogen on the right, it has a duet, it's satisfied. Chlorine up top has 8 valence electrons, it's in good shape. This chlorine has 8 valence electrons. Let's also look at the carbon. Carbon has 2, 4, 6, 8 electrons around it with those 4 bonds, so this carbon is also satisfied. Let's check our other rule. Have we shown all 20 valence electrons? Well, we have 2, 4, 6, 8 from the bonds, and then we have an additional 10, 12, 14, 16, 18, 20. So indeed, we have shown all 20 valence electrons. Everyone's happy, everyone's in good shape. This is a complete Lewis structure. We're good to go. Everyone has a full octet. We've shown all of our valence electrons. All right, let's turn up the heat a little bit. Let's go to CO2. We'll keep our wits about us. Let's keep the same rules in order, right? So let's start with our valence electron calculation. We have 1 carbon. Carbon has 4 valence electrons. We have 2 oxygens. Each one brings 6 valence electrons to the table. Again, column number 6. We need to be showing a grand total of 16 valence electrons. So let's do CO2, and when we set it up, here's what we'll do. We'll put a carbon in the middle, and we'll surround it by 2 oxygens for symmetry. You'll notice that I'm writing towards the top of the box. Go ahead and do that as well. We're gonna put a lot in this box, so make sure you write towards the top. Now our first rule is to add valence electrons to the outer atoms until they have a full octet. So this oxygen already has 2 electrons from that bond. Let's give it 6 more, 2, 4, 6 more, and gives it a total of 8. Same thing over here. We have 8 valence electrons represented. So let's take stock of where we are. Oxygen on the left, happy with 8 valence electrons. Oxygen on the right, happy with 8 valence electrons. Carbon in the middle, not happy right now. How many electrons have we represented thus far of our 16? Well, we have 2, 4, 6, 8, 10, 12, 14, 16. So we have ourselves a pretty massive problem, right? What's our problem? Well, we've shown all 16 electrons. We don't have more to give. We cannot just do this. We can't just add valence electrons, because that wouldn't be showing 16 valence electrons, that'll be showing 20 valence electrons. We don't have those valence electrons to give. So what do? If you run into a situation where you have your terminal atoms filled, and you don't have enough valence electrons to add to your middle atom, right? We're electron deficient, we don't have enough. We need to start sharing. And so what if we do this? Remember, as we take count of these electrons, what was going on. Right now, this oxygen on the left, it has 8 valence electrons. Oxygen on the right has 8 valence electrons. Carbon has 6. So what I'd like to do is try this. We'll write this one in blue. I'd like to swing these electrons in to form a double bond. So let's redraw that and let's see what that looks like. We'll still have our oxygen on the left with 8 valence electrons. We'll still have our carbon in the middle. We'll now have a double bond and this one only has 2 lone pairs around it because that one pair swung in to make a bond. Let's talk about how many valence electrons we have shown. We have 2, 4, 6, 8, 10, 12, 14, 16. We're good. Notice this counts for 4 valence electrons because it's a bond. So we're still showing 16 valence electrons, which is the total we're allowed to show. Let's check the valence. So oxygen over here on the left is happy. It has 8 valence electrons. Oxygen over here is happy. 2, 4, 6, 8 valence electrons. So that one's good. Carbon now. This one's good. Let me write those in. So oxygen on the left has 8. Oxygen on the right has 8. Carbon now has 2, 4, 6. And I'm noticing that I made a mistake earlier. So if you were kind of wondering what was going on, my apologies. The carbon up here doesn't have 6 right now. It has 2, 4. Right? It only has 4. So let me erase that 6 and make that a 4. My apologies. But now we've made things better, right? We're on a trip towards a full valence shell of 8 valence electrons. Currently, we have only 6 on the carbon, so we're not there yet, but things are looking up, right? Because we've gotten it from 4 to 6. If we can do that to the left-hand side, to the right-hand side, why can't we do the same thing to the right-hand side, right? So let's try that. Now we have carbon, double bond oxygen on the right, and we've just established a double bond on the left. Again, with those lone pairs, let's count up. Total first. 2, 4, 6, 8, 10, 12, 14, 16. That's good. We have 16 valence electrons. Oxygen on the left, 2, 4, 6, 8. Oxygen on the right, 2, 4, 6, 8. So both of the oxygens are now good. Carbon, 2, 4, 6, 8. So now we have a situation where our oxygen on the left has 8 valence electrons, our oxygen on the right has 8 valence electrons, and our carbon has 8 just by sharing. And so that works really well for everyone. Now, there's a subtle side note that some of you might be wondering that I should show you briefly, which is this. And you don't need to do this because it's really not a stable arrangement. But after we were at this blue stage, some of you might be wondering, couldn't we just drop this in and make a triple bond? And we would end up with this arrangement. We would have an oxygen on the left that looks like that. We'd have a carbon in the middle. We'd have a triple bond to an oxygen that looks like that. And if you count all those up, everything does have its full octet. You have represented 16 valence electrons. So that does work. And you could actually do the exact same thing going the other way, right? So you could, if you really wanted to, let me find a different color here. You could do it this way as well. We could make that triple bond over here to the left, carbon in the middle, single bond on the right. Again, all of those have a full octet. We've shown 16 valence electrons. It turns out that that is possible. It turns out, though, that the purple one we've drawn in the middle is by far the most stable. So when we can, we want to create symmetry. So yes, those things are reasonable, but ultimately our best Lewis structure, our final answer to our Lewis structure, let me just draw this once kind of clearly so we're all on the same page. Our best answer to our Lewis structure is this one in the middle. It's carbon, it's an oxygen on both sides, both of those having a double bond. Right, so that is our best Lewis structure for carbon dioxide. All right, let's try one more. We're going to go over here to HCN. When we do HCN, let's again come through and let us calculate valence electrons. So there's one hydrogen. It has 1 valence electron. There's one carbon. It has 4 valence electrons. There is one nitrogen. It has 5 valence electrons. If we add those up, we are going to get 10 valence electrons. When we draw HCN, HCN is a little bit unique. Why is HCN unique? Because it's written with H first. So you'd think we could do this. But hydrogen, remember, only likes 2 electrons. And if we do that, it has 4. So hydrogen is this exception that oftentimes it's written first, but it's never in the middle. So HCN is actually written in the order that we should draw it. It's written like this: H, C, and then N. Now, we have shown 4 valence electrons already. We need to show a grand total of 10. So where can those electrons go? Well, we could put them on H, but remember H already has its 2 valence electrons. It only wants 2, so it can't take any more. So we're going to start filling the outer atoms first until they get an octet. Here's nitrogen with its full octet, and that takes care of all of our outer atoms. Let's take stock of where we are. So nitrogen has 2, 4, 6, 8 electrons. It's happy. Hydrogen has 2. It's happy. But carbon only has 2, and check it out, we've already used 2, 4, 6, 8, 10 electrons, right? So we have a problem. We again find ourselves in a situation where we are electron deficient on the middle atom, and we need to get it more electrons, but we can't just add dots. Remember, you can't just do this because you only have 10 valence electrons to play with. So you don't have electrons to make that move. So what can you do? Well, just like before, we can start making multiple bonds. Let's swing this in. Let's see where we go from there. If we do that, we get HC, now a double bond to N. If we count up valence electrons, we have 2 here, 2, 4, 6, 8 there, and now carbon has 2, 4, 6. So we're getting better. Up top, this carbon had 4 valence electrons. Now it has 6. But we need more electrons. And you'll notice we don't have any on hydrogen to give it. We can't swing in any electrons to make a double bond with hydrogen, but we can do another one with nitrogen. So let's do this. Let's make HC triple bond N. Once we do that, our total electrons are 2, 4, 6, 8, 10. So that's good. Our electrons around nitrogen are 2, 4, 6, 8. And our electrons around carbon are 2, 4, 6, 8. So everyone's happy. Carbon now has its full octet. This is the final Lewis structure for HCN, and we are good to go. Now you'll notice here on page 10 there are some more things and some more tricks that we have yet to see. That will come. We'll get more practice and we'll continue filling in this sheet as we go. Just remember with Lewis structures, these rules that we're following in order, right? So we're starting with the outer atoms first, and we're checking at the end of the day to confirm that these 2 statements are indeed correct.